So this is exercise 4C and this is question 7. Now this question here is asking you, let z equal cis theta and show the following. And I've taken something here out of the textbook which is really important that will help us with this question. It's the idea that if z is given by a complex number in polar form r cis theta, which we could think of in rectangular coordinates as being a plus bi, that if you look at its conjugate, z bar, and that's written here, you know that that would be a negative bi. So for example, let's say that we had, 1 plus I for an explicit example. The conjugate would be 1 minus I. So that would be a complex number going up, okay, going across 1 and up I, whereas this would be a complex number going across, but then down I. So it would be a reflection, and you can see that here in the diagram. What that also means is that the angle theta, which you would have in Z, instead of being a positive angle, would be a negative angle because you're going down because of the reflection. So this angle inside here would be negative theta. So that's going to be useful for us in this question. So you can see here, first of all, it says for A, show that the mod Z equals 1. Now we've got Z equals cis theta. All I'm going to do is just expand that out. So we've got cos theta plus I sine theta. That's what Z actually is. That's what the cis form means, and the 1 in front. Now if we wanted the modulus of Z, what we'd have to do is square the real part of the complex number. So it'd be cos theta squared, plus we'd square the imaginary part, sine theta squared. Now we know that cos squared theta plus sine squared theta equals 1. So this is the square root of 1, which is 1. So therefore, you've actually shown that the modulus of Z equals 1. The next part of the question, you can see there you've got a 1 over Z question, and it's asking you to show that 1 over Z equals cis negative theta. Now I'm going to look at what 1 over Z is. Now remember that if this was to be in rectangular form and Z was some complex number, let's say 1 plus I, we wouldn't leave it like that. Remember that we would realise the denominator by multiplying by the conjugate on itself. And that's what we're going to do here as well. So what we're going to do is multiply this by the conjugate over itself. So we're going to have Z bar on the top, and we're going to have Z bar underneath. Now in one of the earlier examples we actually looked at what happens with Z bar, and just with an explicit example here we'd have A plus BI. The conjugate would be A minus BI. Okay, Z bar would be A plus BI times A minus BI. And if we expand that out, what you're going to find is you'll have A squared minus ABI plus ABI, and then minus B squared I squared. They cancel, and you have A squared. This is a negative 1, so this will become A squared plus B squared. Now that looks very similar to this formula, which we know, the modulus of Z equals the square root of A squared plus B squared. So what this actually tells you is this formula here implies the modulus of Z squared would be A squared plus B squared. So this is sort of an interesting link here, because now what you can see, and I'm just going to draw a box around that because that's quite a useful piece of information. With what we're dealing with, we have here Z bar, that is actually A squared plus B squared. So it's simply the modulus of Z squared. So up here in the question, we had Z bar on the top, we had Z bar underneath, so that's just going to be Z bar still on the top. The bottom is mod Z squared, and we actually know mod Z is 1. So that's going to be Z bar over 1. Now since 1 over Z equals Z bar, and we know that Z bar can be given in this form, R cis negative theta, if Z equals cis theta, then that implies that 1 over Z equals cis negative theta because of what Z bar is from here. So you're using this result here that Z bar is the reflection, and you could state that as well. Z bar is a reflection of Z across the x-axis. I've run out of room, but you could state that at the end there as well. So the idea here is working with that 1 over Z, getting it to a form where you recognise, oh, that looks a lot like this, but I need to get this in a particular form like that. And you can see there's a conjugate here. So introducing a conjugate by realising the denominator, this is a very useful identity as well, that the modulus of Z squared equals A squared plus B squared, or More simply, a really nice one to have in your notes is that z bar equals the modulus of z squared. That's a really nice identity to put on your formula sheet in your notes, just as a little reminder for what to do when you have this situation arise.